Welcome back. So the last time we looked at the implicit function theorem and did several examples of it. From this time onwards, for a few lectures at least, we'll do something that's closer to applications. Yeah. So we'll start with a problem that is of interest to people who work in things like optimization, and then move our way through. Okay. All right. So suppose you take an open set U, yeah, in Rn. Let's say it looks like this, yeah, such that U bar is compact. Okay, so this is U bar. Recall, what does compact mean? It means, well, it doesn't mean, but closed and bounded subsets of Rn are compact, and compact sets are always closed and bounded. Okay, meaning that this set is contained inside some large rectangle of finite size, and it's closed. Okay. Right, this is the closure of U, right? So it's the smallest closed set containing U. Now suppose f from U bar to R is continuous. Now, as we have discussed a while ago, a continuous function on a compact set attains a maximum and a minimum. That is, there is some point, maybe let's call it this point, maybe I'll, instead of denoting it as x, I'll just probably use a different letter. There is this, let's say, point, let's say, where f assumes a maximum, and maybe let's use another color, this point where f attains a minimum. Yeah. So f attains a minimum here and f attains a maximum here. Okay. There are two such points. The question is, what are these points? Okay. Can we figure out what these points are? And what the, if we know the values of these points, I mean, we know where these points lie, we know the values of f at those points, right? This is the kind of a question that arises in various situations, including optimization. Okay. So that's in applications. In pure mathematics, it arises, for example, if you want to prove various inequalities. Okay. The famous arithmetic geometric mean inequality can be proven by stating it as an instance of this question. Okay. So this is a rather important question, and we want to answer it. Yeah. Okay. So we've already seen a lemma that helps us. Yeah. So by the way, these things, these are global max and global min, which is simply fancy terminology for saying that it's the maximum over a given compact set and a minimum. Not in general, not even if your set is not compact. If you give me a set and a function, you can ask what the maximum value is if it exists, and what the minimum value is if it exists, and they are called the global max and global min of f over this set. Yeah. So, and these are collectively called as extrema. So we have already seen one lemma. If an extremum occurs at an interior point, point P, and if f is differentiable there at P, then the gradient of f is 0. We have seen this several times. Very quickly, what's the proof? Well, if if the extremum occurs at an interior point, what is an interior point of a set again? As the name suggests, it's a point inside, meaning there is a small ball around, small open ball around this point that lies entirely within this set. So the point is, if you take any straight line, along the straight line, f is a one variable function and it's differentiable, and it assumes an extremum at that point, and therefore the one variable derivative is 0. So that since that's true in all directions, the gradient is 0, right? So this motivates another definition, that of a local max and a local min. You're supposed to know this definition because it's exactly the same definition as the one variable calculus counterpart. So what is the local max of a function? A point P is said to be a point of local maximum of a function if there is a neighborhood of P such that the function is defined on that neighborhood and the values of the function are less than or equal to the value of the function at P. Meaning it is basically a maximum of the function, but only locally, only when compared to points nearby. Okay? When you go far away, then you can have points which can have higher values of f. Okay? All right. So coming back to this definition, so we know what local max and local min are. So the point is, if you want to find the answer to this optimization question of finding global max and global min, all we have to do is assume, find the critical points. What's a critical point of a function? It's a point where either the function is not differentiable in the interior. So either the function is not differentiable, or if it is differentiable, the gradient is 0. And look at the boundary behavior. So the global extrema can either be attained on the interior, and if they are attained on the interior, then either the function is differentiable there and the gradient is 0, or the function is not differentiable there. These are called the critical points. Or it's attained on the boundary, in which case we really don't have any tools at our disposal as of now. Okay? So let us look at an example to see how complicated this can potentially get. Okay? So example, so f of xy is xy on x square plus y square is less than or equal to 1. Okay, so this is the u bar and this is u, if you will. Okay. Okay, so this domain is compact. Why is this compact? I mean, it's what is compact? It's closed. Well, this is a closed set. Why is this a closed set? So the claim is this is closed and bounded. Obviously, it is bounded because mod x is less than or equal to 1, mod y is less than or equal to 1, so it's contained in a large rectangle. Why is it closed? This I leave to you as an exercise. What does it mean to be closed? That means the complement is open. What is the complement? X square plus y square is strictly larger than 1. Why is this open? Because if you take any point x naught, y naught, so that x naught square plus y naught square is larger than 1, if you perturb x naught and y naught a little bit, they will continue to satisfy x square plus y square is larger than 1. Okay? Of course, I would want you to do it more rigorously. That is, I would want you to actually find an open ball of some small enough radius r, so that if this satisfies this condition, then every point in the open ball should also satisfy this condition. That would prove that the complement is open and therefore this set is closed. Since it's easy enough, I urge you to do this on your own. Okay, so this is a compact set. So f does assume a global, a max and a min somewhere. Okay, and f is smooth. Okay, so it's differentiable everywhere. So either the global extrema occur in the interior. If they do occur in the interior, they're all critical points, then gradient of f is 0, or they occur on the boundary, which is x square plus y square equals 1. Okay. Right. So let's compute the gradient of this function and set it to 0. What's the gradient? It's df by dx and df by dy, which is y comma x, which is 0, 0 if and only if x is y and 0. Okay. So there's only one critical point and it occurs in the interior. What's the value of f of 0, 0? It's 0. So let's record it and keep it aside. Now we want to look at the behavior of f on the boundary. We want the extrema of f on the set x square plus y square equals 1, right? Now notice that this is also closed and bounded, this is also compact, and therefore the extrema of f do exist. The question is, how do you find them, right? So one way to do it is to parameterize the boundary like this. F of xy is basically g of theta, which is cos theta times sin theta, because we can take x as cos theta, y is sin theta, where theta is in 0 and 2 pi. This parameterization will cover the entire circle. That is, if you take this set, if you write x as cos theta and y as sin theta, where theta is in 0 and 2 pi, this particular set of points in R2 is exactly the same as this set of points in R2. So if we write x as cos theta, y as sin theta, you can write f of xy as x times y, which is cos theta times sin theta. Now we have reduced our problem to a one variable calculus problem. Okay. There's several ways to do it, right? For example, we can be clever about it. We can say this is sine 2 theta divided by 2. So obviously this is less than half and this is larger than minus half. I mean, it's equal to half when 2 theta equals pi by 2, and it's equal to minus half, for example, when let's instead take minus pi and pi. That will make our job a little bit easier. Well, this is 2 theta is minus pi by 2, right? So in other words, so we have 3 candidates for the maximum and minimum values of f, right? Namely, this one, and when 2 theta corresponds to pi by 2, 2 theta corresponds to minus pi by 2, we get half and minus half. Obviously, this is the largest value of f and this is the smallest value of f. So in other words, when 2 theta is indeed pi by 2, that is theta is pi by 4, what is x? X is cos theta, which is 1 by root 2, y is 1 by root 2. Here it's minus pi by 4, so x is cos theta 1 by root 2, y is minus 1 by root 2. So at this point, we have a global minimum. At this point, we have a global maximum. But by the way, these are not the only points where we have global. Actually, sine 2 theta is 1, not just when 2 theta is pi by 2, but when 2 theta equals something else as well. Could potentially be something else as well. Right? So that I'll leave you to think about this a little bit more. But the bottom line is, the maximum possible value of f on this domain is half, the minimum possible value of f is minus half, and the maximum possible value can be attained at multiple points, minimum possible value can be attained at multiple points as well, right? What is important to note is that the place where the gradient is 0 is only a local extremum and it doesn't play a role whilst computing the global extrema, right? Okay. So this is a rather complicated affair, right? Because it's sort of easy to find out where the gradient is 0. The trouble is, when you go to the boundary, then what you are trying to do is to find out the maximum or minimum possible values of a function subject to a constraint. Okay. I mean, even this is subject to a constraint, except that this constraint is lying on a set, lying on a set, on a level set of a function, right. What we mean is, we can abstractly phrase this problem as, find the extrema of f subject to the constraint g equals 0. Okay. This problem plays a role in this situation, right. It's unavoidable. Now, look, luckily in this particular situation, we could explicitly parameterize this set in a nice way and reduce ourselves to a one variable calculus problem. Note, however, that suppose we had a 3 variable problem. Suppose instead of f of xy equals, let's say for the sake of argument, suppose I take f of xyz as xyz and I demand find the global max and min on this set, right. Then you will first find the gradient and set it to 0, you will get some point, then you will look at the boundary. And this is a very nasty affair, right. The reason is, here you can't simply parameterize the boundary by one variable. You might have to use, for example, cos theta, sin phi, cos theta, say cos phi, and let's say sin theta or some such thing, right, spherical polar coordinates. Now, you would have reduced your 3 variable problem to a 2 variable problem, right. Then again you would have to apply the same algorithm and check where the gradient of this 2 variable function will be 0 and see what happens to the boundary, which will be a 1 variable problem, right. So, if you have a 25 variable problem, you can reduce it to a 24 variable problem on the boundary and looking at the gradient on the interior. Then on the boundary again you might have to reduce it to a 23 variable problem and so on. It's a mess, right. So, this question, constrained optimization, it's playing a role, that is, find the extremum of some function subject to some other function being 0. It's playing a role in global extrema, but the trouble is we don't seem to have an efficient way to solve this problem, okay. For 2 reasons. One is, as I said, if you have a 30 variable problem, you will have to inductively keep reducing the number of variables, right. And the other problem is, you can't always explicitly parameterize sets, right. Luckily, x square plus y square equals 1, you can write it as x equals cos theta and y equals sin theta, or you can solve for y in terms of x or some such thing, but you can't always do this. You can't always find such a neat little formula. So, we seem to be in a fix, okay. So, we need a better way of handling this whole story, and that is where this method of Lagrange's multipliers comes in, okay. So, right. So, the point is, so there are 2 problems here. One is, we might have to inductively reduce the number of variables several times. This is one problem. The other is, we may not be able to solve the constraint explicitly. That is, we may not be able to solve for some of the variables in terms of the others by means of a nice little formula. But, so how can we handle this? This part at least, the implicit function theorem might help, because even if you can't solve for one of the variables in terms of the others explicitly, The implicit function theorem will at least guarantee under some circumstances that there is a solution. It's just that you can't write a nice formula for it. But that's not very helpful, right? It seems like it's not very helpful. Herein lies a wonderful method due to Lagrange. This is called the method of Lagrange's multipliers. So the theorem is, let f and g from an open subset of Rn to R, it is crucial that this be an open subset, be C1 functions. Why is it crucial that it be an open subset? Because we have defined differentiability for open subsets, right? Assume that A is a point in U, and it is a point of global max or min subject to g equals 0. Suppose at this point the gradient of the constraint is not 0, then nabla f at this point is lambda times nabla g for some lambda in R. This lambda is given a name, it's called a Lagrange multiplier. Okay, so what is this saying? This is saying, suppose you have two C1 functions on an open set, and suppose you have a point, let's maybe draw a small picture. This is an open set, and if you take the constraint g equals 0, presumably it's something like this. This is g equals 0. Suppose you have a point A here such that, and let's say the gradient of g of A is not 0. This is a global, it's a point of global maximum or minimum of f subject to this. That means if you look at all the values on this curve, g equals 0, which lie in U, you look at the values of f, okay, and f of A is the maximum or the minimum of all such values, okay. So that's what it means to say global maximum subject to a constraint. Suppose A is such a point, then the gradient of f at that point is proportional to the gradient of g. Obviously, g of A is also 0. Okay. This has not been written, but it's understood from what's said. So in other words, you have, if you know that A is a point of global maximum min subject to g equals 0 and A lies in the interior of U, then at that point you have a few set of equations you need to solve. G of A is 0 and gradient of f of A is lambda times gradient of g of A. So in other words, you have enough, I mean, on paper, what are the unknowns here? A is unknown and so is lambda. This is an unknown in Rn, so you have n plus 1 unknowns, but this is one equation and these are n equations, so you have n plus 1 equations. So it is reasonable to be expect that we can solve for both A and lambda, okay. So that is the method of Lagrange's multipliers, all right. So we will use the method of Lagrange's multipliers in just a moment, but let us look at the proof. The proof, I mean, you might think that the proof would be a rather formidable affair, but it actually isn't. It's exactly what you would expect it to be, okay. So the problem here, so how does one prove this? The aim is to convert this constrained optimization problem into an unconstrained one. Constrained one by solving the constraint. what does this mean? Now, since gradient of g of a is not 0, right, that means dg by dxi of a is not 0 for some I. Okay. Now, without loss of generality, that I equals n, that is the grade dg dxn of a is non-zero. If it is not n, right, the same argument would apply anyway. Okay, it's just simpler to just assume it's n. Otherwise, the same argument will apply anyway. Okay. Now the point is, by the implicit function theorem, since this is the case, locally we can solve the constraint g equals 0 to get xn as a function of the other few variables. Okay, I'll make this precise. What does this mean? What this means is there exists a neighborhood, let's call it W, in Rn minus 1 of this point a1 to an minus 1, and a neighborhood of this form v equals w cross an minus epsilon and an plus epsilon of a, and a C1 function h from w to r such that g of x is 0 if and only if xn is h of and xn is in v if and only if xn is a function of these. That is, we have solved for the constraint locally. That means near all for all points near this point a, we have solved the constraint to get the last variable as a C1 function of the other ones. Okay. How does it help? So, if you consider this function s of x as f of x1 to xn minus 1, maybe let us call it s of x1 to xn minus 1, comma h of x1 to xn minus 1, that is, you have solved for the last variables. This function s attains a local extremum at this point. Why does it attain a local extremum? Well, let's look at the hypothesis. The hypothesis is basically saying that A is a point, it's a point of global, but in particular it's a point of local extremum for f subject to this constraint. And we have solved the constraint. What does this mean? For all x1 to xn near a1 to an minus 1, this function is either larger than or equal to its value at a1 to an minus 1 or less than or equal to its value at a1 to an minus 1. Okay, so it attains a local extremum. If it attains a local extremum, then we know that the gradient of this is 0, right? That is, what is the, for example, what is ds dx1? By the chain rule, we apply the chain rule to it. This is df dx1 plus df dxn dh dx1. Okay, that's how the chain rule works. That is 0 at this point. Okay. Likewise, this is true for any I. x1 was not special here. Okay. So, because it's a local extremum, the partial derivatives of s at this point a1 to an minus 1, maybe let us call this a tilde. Okay. At this point are 0. And how does one compute the partial derivatives? One uses the chain rule. Okay. So, we are out of time. We will continue with this calculation the next time, right, and we will then prove the theorem of Lagrange's multipliers, and then we will move on to some examples. So, we will continue the next time. Thank you for joining.